Hi, I'm Max Orton. I'm 17 and a senior at Northwest Academy in Portland, Oregon. This is a quick presentation showing a derivation I have for why the radius of a circular classical relativistic string follows a sine wave as it evolves. It's super fun. It's the third derivation of that fact that I've so far created, and it's by far my favorite. It's almost entirely geometric, and it uses a Wick rotation and the catenary problem of all things. It ties a whole ton of things together, and it's super fun. So that's what I'm presenting here. Thanks so much for watching. First thing we can note is our Lagrangian, which is where the action is proportional to the surface area of all the strings, where this constant is just negative the mass density. For all intents and purposes, we can just say that action is proportional to total surface area. So this is, of course, relativistic surface area in space and in time, and it is related by a Wick rotation to normal four-dimensional space surface area. So that is the crux of this argument, is using a Wick rotation to shift ourselves from Minkowski space into normal four-dimensional Euclidean space and then solve everything there. We can also say that we have a string that exists just in the xy plane in a circle, since this is for a circular string. And I'm going to need to switch my x and my y here. And since it's going to stay in a circle because our action is rotationally symmetric across any axis, we can just ignore the z-axis for now. So we'll just be dealing in a two-dimensional plane with x and y, and then we can draw time going into the third dimension. So all of that together means we can start off with some initial string configuration and some initial velocity, and there'll be some world sheet connecting this to a final string configuration over at some later time. Our next goal is to Wick rotate this. We're not going to do it very formally. To do it formally, I would have to write out more in detail what the action is. We're just going to say that that surface area, when Wick rotated from Euclidean space to Minkowski space, or vice versa, just switches the corresponding formulas for surface area. So we'll make a Wick rotation right here, and then up here we say action is proportional to area. Down here, action is still proportional to area. We pick up a factor of I, but that won't matter when we're minimizing the action. Over here, I'm drawing a very suggestive diagram of what this is going to look like, but it goes something like this. And this is the minimum configuration in our Euclidean surface area, which makes some sense because the two forces controlling this is that you want this to take the minimum path length from A to B. That would shorten this, but it also picks up extra action when it's large. So in between the two endpoints, it's going to want to contract some. So that is this. And we are going to a little bit more formally write out our second action, just a tiny bit. Enough for us to reason about yet another system that this is equivalent to. So we can break this, I sort of already did with this diagram, we can break this into a bunch of little steps and write the action as an integral over these steps. Now remember, this definition is time. I'm going to call it tau, where tau equals it. But either way, it's an integral over something like time, has units of time in natural units, which means it doesn't really mean much, but still. And what we're integrating over, our surface area of any one of these sections is going to be proportional to its radius, r, and it's going to be proportional to how long the section is, L. So we can call L R, where both R and L are functions of tau. And we're looking for the radius R as a function of tau. That's what we're going to Wick rotate back to get our R of t function for the string, the relativistic string in 4D Minkowski space, 3 3-ish, 4-ish d Minkowski space. So what we're going to see is that this is equivalent to the catenary problem. So if you have a hanging string here, I'm going to make sure it connects between the two endpoints and is hopefully at least a little bit symmetric. You can break it into a bunch of different sections. And each of these sections is the potential energy for this section is going to be mass, gravity, height. Height is some function, and then gravity is a constant, and mass is proportional to the length here. So this is all going to wind up as length times height. And so the potential energy V will be an integral of length, height across x, which is my horizontal coordinate here. Now these look pretty similar. In other words, minimizing this potential energy, which is where the string would be stationary, hence the catenary problem, is going to give you some function h of x. And that's the exact same minimization problem that you're doing to get the function r of tau from minimizing this action here. So we can ignore this for a second, relegate it to the bottom here, and just think about the catenary problem. How will a hanging string hang? Fortunately, we know the answer to this problem. This problem's answer is going to be something times, I'm running out of room, so we are going to erase the definition of potential energy, right, that h of x is equal to something times hyperbolic cosine of x minus, I'll call it x naught, over something else. So that's where we are now. And that means that in this one step up the layer of jumping between systems backward, we can say that r of tau equals the exact same thing, a hyperbolic cosine of tau minus tau naught over a. It's worth noting, we've been working in natural units for this whole time, so c equals 1. That's why I could say that tau equals it, and that's also why this isn't a little bit odd to have units of length and units of time here interacting. Units of length and units of time are the same in this case, since we're working in natural units. Either way, we now have a function for r of tau, so we can plug in yet more and say that we can Wick rotate backward to our case of relativistic strings in 3-ish, 4-ish d Minkowski space. So Wick rotation here, and we get that our original function r of t, which is this function down here, r of it, is all going to evaluate out to be equal to a cosh of, here we have it minus, and then I'm going to call tau naught I t naught over a. I'm now erasing this definition down here. And then we can bring the I out, and we can say this is a cosine of t minus t naught over a. Now, this is essentially the same formula that we derived in my STEM portfolio with the write-up related to relativistic strings, where I did the calculation about a circular relativistic string. And it's amazing that we can get here just with Wick rotation, knowing the answer to the catenary problem, and a little bit of reasoning and guesswork. We can, to make it look even more like the solution, we can call A R naught, because it's going to be the initial and maximum radius. And we can finally write all out in its full glory that R of t equals R naught cosine of t minus t naught over R naught. And this is the formula for the radius of a circular relativistic string as a function of time, and I find it absolutely amazing that we can derive it without needing to ever even pick an explicit form in terms of square roots and derivatives for our Lagrangian. We can just go one step of geometry to another and get all the way here.